Okay, term assessment 2, question 2. Okay, question 2, we have a reaction scheme of ethanol being converted into a number of reactions. So, for such a question, because we are looking at reagents and conditions. Alright, one important thing to take note is the number, or rather the functional group change along the way. So, for this compound, you have a primary alcohol, which then becomes an aldehyde. So you can see stage 1 involves an oxidation reaction. Okay, and in this case it's a mild oxidation because primary alcohol becomes an aldehyde. This will guide you in terms of your reagent conditions required for stage 1. That's your dichromate acidified with sulfuric acid, and you need to heat with immediate distillation. Okay. Okay, if not, your aldehyde will further oxidize to carboxylic acid. Now, take note, I cannot accept KMnO4, or rather, we cannot accept KMnO4 because KMnO4 is a very strong oxidizing agent. It will bypass the aldehyde stage directly. It will go straight to carboxylic acid. Now, later on in stage 2 is something that you are not aware of. There's no such reaction you learn in the syllabus, but you know that it combines to form A, and A basically have an alkene and an aldehyde functional group. But what we do know is that in stage 3, the alkene is reduced and the aldehyde is also reduced to form a primary alcohol again. So you can see it's a concurrent reduction of both alkene and aldehyde. So think through all your reducing agent, what can reduce both alkenes and aldehyde concurrently? It's only your hydrogen gas. Okay, hydrogen gas, whether you use it platinum palladium at RTP or platinum or nickel catalyst at high temperature and pressure. In this case, we cannot accept lithium aluminum hydride or sodium boron hydride because alkene is also concurrently reduced. Your lithium aluminum hydride and sodium boron hydride will only reduce your aldehyde to your primary alcohol, but it cannot reduce alkenes. Alright? Okay, so if not, then we move on to part 2. Part 2, basically, it's a simple deductive question starting from compound A. So compound A is this formula here. Undergoes a reduction reaction with compound B. We're supposed to deduce what's the structure of B. So B gives an effervescent sodium metal, but does not react with 240 pH and also declares aqueous bromine. So take note, A starts from this. A undergoes reduction. So the two functional groups that can undergo reduction are your alkenes and your aldehyde. So since it gives an effervescence with sodium, it's your acid metal displacement reaction. And because you have an aldehyde functional group, when it's reduced, it can give you an alcohol, right? And in this case, to be more exact, it will be a primary alcohol that undergoes acid metal displacement with sodium. It cannot be carboxylic acid because the context is that B is a reduced product of aldehyde. So aldehyde will become a primary alcohol. Okay? Now we move on. It does not undergo any reactions with 240 pH. So the type of reaction is your condensation reaction with 240 pH. Okay, type of reaction is 240 pH with condensation. So the absence of your aldehyde and ketone. Again, we cannot accept carbonyl group because carbonyl group is not a functional group. Similarly, alcohol, it's a functional group, but OH is not a functional group. Hydroxy is also not a functional group. Okay, the type of reaction with aqueous bromine then. Now, in this context, because we are looking at compound A as a starting reactant to form B, it's the question of whether the alkene is present or not. So, I have no idea why so many of you focus on the phenylamines. That's not valid. So, in this case, it will be an electrophilic addition reaction. Your B therefore contains an alkene since it decolorizes equals bromine. So, these are the deductive statements. There are 6 deductive statements. You get 2 marks if you get any 4 correct. Okay, and therefore, since it's an alkene, it has an alcohol. The compound B will therefore be the alkene is not reduced, and the aldehyde is reduced to a primary alcohol. So the alkene remains intact. The aldehyde, you can see the aldehyde, alright, is reduced to a primary alcohol. That's the structure of B. Okay, that's done with 2A. We move on to 2B, which is the application question. So 2B basically is continuation of the reaction. You are given 3 steps. You can see that in this process, step 1, it's an acid-base reaction. The OH minus basically acts as a base. The H here is gone, as a H plus, the OH minus to form water. So this CH bond is broken. The lone pair here grabs the H, and this CH bond is broken such that both electrons are given to this carbon, and that's why you have a negative charge on this carbon. And this negative charge here follows a nucleophilic addition reaction. So with a lone pair here, alright, undergoes nucleophilic addition mechanism, right? So you have a nucleophile here, the delta plus carbon here, delta minus here. So lone pair attacks this delta plus carbon. This CO bond, pi bond breaks, and you form an intermediate which then becomes 3-hydroxybutanol. And then later on, elimination of water is occurred. And in this case, elimination reaction, you have a double bond here. This is where the water comes out as H2O. Okay, so just a quick understanding of the mechanism. We're supposed to draw a mechanism for step 2. So using the given structure. Okay, so you can take a look at what I've drawn earlier on. This is the nucleophile, this is the electrophile, the carbonyl compound. So same thing. Now instead of skeletal formula, they give you an expanded structure formula. So first thing first, draw in your lone pair. Delta plus, delta minus. This is therefore your electrophile, because it has an electron deficient carbon. This is a nucleophile because this is electron rich. Nucleophile attacks the electrophile. So arrow draws from the lone pair to point to the electron deficient carbon atom. Lone pair, arrow pushing from lone pair to the electron deficient carbon atom. Alright, then you have your delta plus, delta minus, that's a dipole to identify which is the electrophile. And then you show your CO bond breaking. That's a classic nucleophilic addition mechanism, first step. And this step is a slow step. So that's point number 4. The intermediate will have a O minus. That's a result of this CO bond breaking. So just let me color code for you. This C double bond O here. Okay, and then you attach this entire purple fragment onto the electron deficient carbon just now. Alright, so this is the fragment here. The next step is that we need to form 3-hydroxybutanol. So you see that 3-hydroxybutanol is formed when we have added in water. Okay, so this is 3-hydroxybutanol. So you can see we have somewhat similar to 3-hydroxybutanol, just that we have O minus. So since there's water, water can provide the proton because it's delta plus H. So put this intermediate next to it. Lone pair of this O attacks this H. This OH bond breaks. Dipoles shown. Arrow pushing. And you form your 3-hydroxybutanol. And to balance this equation, which many of them miss out, you end up with a lone pair on the O. You lose a H plus, and therefore you generate a OH minus byproduct. Okay, this step is the first step, but in this case, the label of first is redundant. Okay, so there are altogether 10 marking points you're looking at. Anything to do with 8 to 10, you get full credits. 5 to 7, you get 2 marks, and then 1 mark if you get 2 to 4 ticks. Okay, so I will zoom out for you to pause the video, take a quick snapshot of this for you to make your corrections before I move on to the next part. Okay, moving on. So why a reciprocal mixture of 3-hydroxybutanol is formed in step 2, and draw the structure of the stereoisomers formed. So let's take a look. In step 2, this is the reaction mechanism. You end up, I hope you guys can see, you end up with a chiral carbon over here. This is the chiral carbon. And it is very obvious that this chiral carbon happens to be the delta plus carbon of the carbonyl compound. So you can see this nucleophile can either attack from the top and the bottom of this sp2 trigonal planar carbonyl carbon atom, from top and bottom of a plane with equal probability. Okay, so take a look. Many of you have similar concept. Nucleophile can attack the sp2 hybridized trigonal planar, but in this case, many of you wrote the wrong term. It's not the carbocation, but the carbonyl carbon atom, from the top and the bottom of plane with equal probability. Okay, and this, where is this covered? It's basically in your mechanism, in your carbonyl compounds, page 13 lecture notes. Right, equal probability of the nucleophile attacking the trigonal planar sp2 hybridized electron division carbonyl carbon atom from top and bottom of plane, which is to equal amount of plus and minus in table, formation of racemic mixture. That's why it's optically inactive. Alright, racemic mixture. See? Alright, so it's bookwork. So draw your enantiomers. Enantiomers, we often have to use your dash and match. So again, focus on drawing your carbon backbone, and you do your mirror plane. Okay, and then fill in your substituents. Okay, so let's take a look at substituents for 3-hydroxybutanol. 3-hydroxybutanol is the carbon. One substituent here, CH2CHO, CH3, OH. Now over here, some of you have issues with representing the aldehyde functional group. Aldehyde functional group is write as, this is the aldehyde functional group, right? We do not write COH. Alright, the correct representation of aldehyde functional group is CHO. Okay? Okay, and last part, which is the more demanding application question, you're supposed to find a way to synthesize this carbonyl compound. So if you take a look at the pattern earlier on, from the mechanism given to you, if I mix two of the same aldehyde, two of the same aldehyde, I'll get this compound here. So you can see that basically where does the joining happens? The joining happens over here, right? This belongs to the CH, okay, so just do some color coding on. This belongs to this part here. Okay, and then this one belongs to this other aldehyde, which is the electrophile. Okay, so I'm going to use the same pattern to illustrate this. Okay, so you can see, because where did the O go to? Because the OH is formed and it undergoes elimination. So from the same pattern recognition, this part here belongs to the one, right, negative charge. And then this part here must belong to the electrophile. So how do I get electrophile? Is when I get an aldehyde. Okay? And of course, to convert this to carbonyl compounds, because the question asks for carbonyl compounds. Carbonyl compounds are compounds with C-double-bond-O. So this should be a ethanol. Okay, so let's take a look at the process. You have ethanol. With OH minus, you form a CH2 minus CHO, right, and H2O. Right, you have your benzaldehyde, this one attacks. You get this compound. So if those of you can see, basically, same process as earlier on. Delta plus, delta minus, the lone pair here attacks this carbon, CO bond breaks. You get this intermediate here, O minus, and then with this compound here. Alright, and then with water, it becomes OH, and therefore you get this compound. And then what happens is that this then undergoes elimination. Remember, we talked about elimination just now. With the adjacent hydrogen, this undergoes elimination and form your double bond. So therefore, what are the two aldehyde groups that you need? One, or what are two carbonyl compounds you need? And two. And that's why these two are the structures. Okay, that's it for question 2.